The Appropriations Subcommittee on Commerce, Justice, and Science will come to order. I would like to welcome our two distinguished panelists, Dr. Charles Elachi, the Director of the Jet Propulsion Laboratory, and Dr. Jonathan Lunine, the Director of the Cornell Center for Astrophysics and the Planetary Society. I am delighted. We are very pleased to have you here with us today to talk about the future of one of the most exciting areas of looking into the future of space exploration, the Ocean Worlds program that this committee put in place in last year's bill to open up new frontiers of in the search for life, where it will be the most, I think, promising. And we're going to discuss that with you today, and I appreciate so much you taking time to be with us. I understand, Dr. Elachi, you want to keep your testimony, verbal testimony, to a minimum, because we don't want you to get complete laryngitis. Dr. Elachi is being honored tonight. We want to make sure he's got enough voice for that, for your acceptance speech tonight. We live in an extraordinary time where the scientific community has revealed to the world that there are as many Earth-like planets as there are stars in the sky. The amazing discoveries that Kepler has made to discover not only Earth-like planets but solar systems and everywhere we look, and the possibility for life on those other worlds and indeed within our own solar system has become very, very real. So today we're here to talk about that search for life beyond Earth, the search for Earth-like planets, the need to develop next-generation rocket propulsion to enable us to reach the outer solar system more rapidly and lay the foundation for interstellar travel so that our children and grandchildren will actually have the reality of being able to reach Alpha Centauri and beyond. I particularly want to welcome our first witness, Dr. Charles Elachi, the Director of the Jet Propulsion Laboratory. It's been my privilege to know and work with ever since we first met in 2004 with the opportunity, at the Mars Opportunity landing in January of that year. We have, over the years that I've gotten to know Dr. Elachi and work with him, I've come to see that I think, quite frankly, the Jet Propulsion Laboratory is the gold standard for NASA flight centers. The work that you do is extraordinary. The way that the Caltech and JPL work with NASA is, I think, a model that I'd like to see replicated at other flight centers around the country. Your collaboration with the National Science Foundation and MIT has most recently led to confirmation of a theory that Albert Einstein came up with 100 years ago about gravitational waves, something I'm looking forward to getting briefed on when I come visit you again in the near future. The discoveries you've made are just absolutely extraordinary. JPL in particular, NASA has developed, and with JPL taking the lead in creating the mankind's first interplanetary data relay system with the constellation of satellites and landers that you have in place around Mars, and it's just absolutely extraordinary. The Opportunity lander, in fact, that I was there with you in January of 2004, is still thriving and doing well after all these years, making great discoveries. And we will, I want to make sure the committee's aware Dr. Elachi has just announced his retirement. Your successor will be in the same position, I think, that Thomas Jefferson was when he discovered that Benjamin Franklin was retiring as the American minister to France. Someone asked Mr. Jefferson about replacing Dr. Franklin, and he said, "No one can replace Dr. Franklin, I can only succeed him." And your successor will be in the same position, Dr. Elachi. Your contributions to the country, to the exploration of outer space, and to pushing the frontiers of human knowledge are just absolutely unparalleled. And it's been a great privilege for me to get to know you and work with you and all the great team that you've got there at the Jet Propulsion Laboratory. We have, and your successor is also going to have to manage, as you do so beautifully, to pull off not only the weaving together all of the scientists, the engineers, being able to work with with elected leadership, and you know you'll have the support of this committee, and your successor will have the same level of support that you have always had. I want to be sure to also welcome and thank Dr. Lunine for being with us today, who is the David C. Duncan Professor in Physical Sciences and the Director of Cornell's Center for Astrophysics and Planetary Science. And you have a particular interest, I know, Dr. Lunine, in how planets form and evolve, what processes maintain and make habitability possible, and what kind of exotic environments might host the chemistry that would be consistent with the evolution of life. And one maybe in the form that we know and perhaps in others. I'd be interested to hear your thoughts on that. We have in our bill, the 2016 appropriations bill, and in previous bills, made certain by law that NASA is going to fund and fly the mission to Europa that the Planetary Decadal Survey recommended last decade as a top priority, and then this decade as a priority right there with the Mars cache mission, which is, and we have made that mission a top priority because it is the top priority of the Decadal Survey, but also because it holds the greatest promise for discovering life on another world. And I want to discuss that and how important that mission is and why that moon of Jupiter is the place we will most likely, in your opinion, find life on another world in our own backyard. NASA is uniquely positioned to explore our universe. It's the only government agency that pushes the boundaries of our knowledge by sending humans and machines beyond Earth to explore and discover. NASA's image among the American people is the American people's perception of NASA is so positive and so high that the only other function of the government that even comes close to them is the United States Marine Corps. In a wonderful nationwide survey that I saw of when you think about the government, which agency of the government has the greatest recognition and positive feeling? It's NASA and the United States Marine Corps. But unfortunately, once again, the Office of Management and Budget has given us a 2017 request that cuts the planetary science budget, that cuts NASA below the level funded by this committee and the Senate. Very disappointing and aggravating. It's why we included language in the financial services portion of the bill that makes it clear that the agencies of the federal government have to follow the appropriations bill, and they cannot follow the budget. So it's important for you to communicate to your colleagues that they should just frankly ignore the budget recommendation. Don't be concerned, don't be alarmed by what they read in the budget. Follow what's in the appropriations bill. My good friend Mr. Honda and Mr. Fatah and the members of this subcommittee are going to make sure that we take good care of the scientific community and NASA. The Decadal Survey, in my mind, has always been the gold standard that NASA should follow. They do a superb job of prioritizing missions, having the scientific community, the experts get together and decide which missions are the most important, and then they prioritize them. And if I could just take a moment before I wrap up and hand it over to recognize my good friend and ranking member, Mr. Honda. The Decadal Survey for 2013 to 22 states in relevant part that if NASA's planetary budget is augmented, then the program will also carry out the first in-depth exploration of Jupiter's icy moon, Europa. This moon, with its probable vast subsurface ocean, sandwiched between a potentially active silicate interior and a highly dynamic surface ice shell, offers one of the most promising extraterrestrial habitable environments in the solar system and a plausible model for habitable environments outside of it. The Jupiter system in which Europa resides hosts an astonishing diversity of phenomenon, illuminating fundamental planetary processes. While Voyager and Galileo taught us much about Europa and the Jupiter system, the relatively primitive instrumentation of these missions and the low volume of data returned left many questions unanswered. The Decadal Survey goes on to say, major discoveries surely remain to be made. The first step in understanding the potential of the outer solar system as an abode for life is a Europa mission with a goal of confirming the presence of an interior ocean, characterizing the satellite's ice shell, and enabling understanding of its geologic history. My colleagues, ocean worlds, and in particular Jupiter's moon Europa, hold many extraordinary discoveries that are yet to be made. We now know, of course, about the ocean of Enceladus, and want to be sure we hear a little bit about that as well. But in particular, I'd like the witnesses to focus on the importance of the Europa mission and why it's so critical that we go to Europa and what we're likely to discover there and what type of launch vehicle we want to use. But before we proceed, I would like to recognize my good friend, Mr. Honda, for any remarks that he would like to make.
Well, thank you, Mr. Chairman. And can you be a little bit more excited about this hearing, please? You can tell, right? It's like Christmas Eve. I want to thank you, Mr. Chairman, and thank you, Dr. Elachi and Dr. Lunine, for joining us this morning to testify on this very exciting topic, and it's really an amazing time to be alive. We're living for the first time in human history where we have the technological ability to actually seek out and find signs of life beyond Earth. And it's like science fiction. And here we are today actually discussing the NASA missions that will do just that. It's truly inspiring. And from the hundreds and hundreds of planets around distant stars discovered by Kepler telescope to the discovery of flowing waters down a crater on Mars, to the discovery of the prevalence of liquid water on at least a half a dozen of the moons of Jupiter and Saturn. The last decade has been filled with tantalizing scientific discoveries that are screaming for astrobiologists and humanity to go exploring, and sort of sets the stage for that movie, The Martian. And that is exactly what we're going to be doing. Second, perhaps only to my chairman, is my excitement for NASA to forge out into our outer solar system and begin a series of missions to explore the water-covered moons of Jupiter and Saturn, the so-called ocean worlds, and seek out the signs of life. It is time to have missions that are dedicated to searching for the clues and signs of life that may have evolved in these alien worlds. Missions to Jupiter's Europa are just the first steps. Saturn's moons of Enceladus and Titan are also calling out to us as we search for life beyond Earth and seek to understand the potentially habitable environments of other worlds. And we're not talking about a one-and-done Europa mission, but instead a series of missions to the ocean worlds to probe their environments for habitability, to see if it's habitable, and potentially signs of life. The extreme diversity and resilience of life on Earth has shown us that wherever there is water, organic compounds, and energy, there is life. Each of these ocean worlds have these three prerequisites for life, and I guess we need to know, does this mean life may have developed there, or do we have neighbors, or is there more to life forming than just having the ingredients as we understand them today? I'm excited to play a witness as we journey out and see what bizarre and magnificent discoveries await us on Europa, Enceladus, Titan, and the ocean worlds. And truly, for someone like me who was here before television, when radio was just a crystal, that to go beyond the confines of this planet and watch these kinds of things unfold is really a privilege to be part of this process. Thank you, Mr. Chairman.
Thank you, Mr. Honda. I feel the same way as I know Chaka does, and all of us in the subcommittee are extraordinarily supportive of the work that you do. Dr. Elachi, Dr. Lunine, we're delighted to have you with us today. And we'll start with you, Dr. Elachi, and of course, without objection, your written statement will be entered into the record in its entirety, and we encourage you to summarize, particularly in light of the fact that we don't want you to lose your voice entirely. But thank you so much for being here, and Dr. Elachi, you're recognized.
Thank you, and Chairman Culberson, Ranking Member Honda, distinguished members of the committee. Let me start by apologizing about my voice. My doctor prognosis is that I talk too much, but that's not stopping me, to come and talk to you here. And it's a great honor for me to have this opportunity to talk to you about exploration of life in the ocean world. Just thinking about it, that for thousands of years our ancestors looked up in the sky and wondered if there is life. And for the first time in human history, and I repeat, as was said, the first time in human history, we know how to do that. We have the technology and the capability to explore for life in our solar system and beyond. And it really depends on us. It depends on you as our leaders and policymakers, and it depends on us as a technical people, be it at NASA, in academia, and in industry. In addition, we know where to look. And I'm going to touch on two locations, and my friend and colleague, Professor Lunine, will touch on two other locations. First, let me talk briefly about Mars. With Spirit, Opportunity, Curiosity, and the spacecraft we have in orbit, we are convinced now, on scientific ground, that actually there used to be oceans on Mars in the past. And then with the changes of the climate on Mars, the water is frozen, now. And the key question is, there was ocean in the past, and based on curiosity measurement, Mars has all the ingredient that exist on Earth. Could life exist? And that's what we are doing through the Mars program, looking for past life, on Mars. And as you know, we have Mars 2020, which is preparing with biological instrument to look and collect samples so they can be brought back to Earth in the following decade. And NASA in the budget has submitted what's called Mars precursors, which basically to prepare for that era, to have the orbiting satellites that are needed, and to look at how do we bring those cache back, how do we explore and prospect for ice in preparation for a human mission. As was mentioned about the Martian, one thing I like about the Martian, that could happen during my children's lifetime. And NASA is putting in place all the elements which could enable us to explore, that planet. Now, the reason we're in such a good shape in Mars is because NASA developed a well-thought, integrated program. And that's the kind of program we need to do the exploration of the ocean world, in the outer solar system. Now, based on Voyager and Galileo data, we do know that Europa has an ice shell, H2O ice. People keep asking me, it's water ice, like I'm drinking, here. And it has an ocean below the surface, which have enough water, which is 2 to 3 times the water which is on Earth here. Now, you would say, how could that be? It's so cold out there. How could there be liquid water in that location? Well, it turned out as these planets or satellites like Europa go around Jupiter, which is a very heavy planet, it's about 300 times the mass of Earth, it creates tide, exactly like what happened with our moon. So over millions of years, that tide has been pumping that ice back and forth, and that's what leads to generation of the heat. So there it has the right ingredient where you have liquid water today, it had organic material, and there is energy coming from the tide. So it has all the ingredients that life could exist, today, not in the past. Now, in order to successfully look at that life, I think we need basically to land on the surface, melt our way, and get down to that ocean. Now, we cannot do that today because there are a number of things that we need to learn before we can do that ultimate mission. So in order to be successful, I think there are 3 elements that need to be done in the near future. One is to have an orbiter which will map the surface of Europa at very high resolution and sound through that ice so we can determine how thick it is. And that's what NASA is planning with the Europa mission that through your direction and NASA the decadal. NASA today has the instrument selected. We are in phase A, and I think we're progressing, with that mission. The second element is to put a modest lander on the surface so we can determine the characteristics of that ice. So between the combination of the sounding, which tell us how thick, the lander, which tell us the characteristic of that ice, that will prepare us in the future to put, if you want, a Europa Ocean Explorer to melt our way and go below the surface. NASA has started that activity based on your direction. Just a couple of days ago, they requested from the science community of people who are interested to be on a science definition team to work with us on defining scientifically what should be the payload. And that lander will capitalize very heavily on what we have done on Spirit, Opportunity, and Curiosity in the technological technique of how do we land with a sky crane. And it looked very much like some of that technology that we have developed before. So we are very confident technologically that with appropriate funding, that mission could be done at an acceptable risk. And the third element is to have a technology program which will support from now to start thinking of how do we melt our way, how do we create a submarine. So by having these 3 elements, I'm confident that we can explore the oceans of Europa in the foreseeable future. Now the next key question is, how do you launch it? How do you get there? And here there are a number of possibilities we are looking at. Clearly, today we have heavy launch vehicles. Those heavy launch vehicles would take at least 7 to 8 years to get us, to Jupiter. And that's what happened on Cassini. What we have to do is to launch, do a series of flyby by Earth to get enough energy to get there. Fortunately, NASA is developing the SLS. With the capability of the SLS, we can get directly to Jupiter in about 2.5 years. That's a huge difference. And to some extent, cost saving from the point of view of the operation. And then you can have combination, depending on how heavy the lander is. If we cannot go direct, we can go and do one flyby by Earth and then head to Jupiter, and that takes about 4 years. So as we speak today, we're looking at all these different options. Now, fortunately, what's elegant about our approach is you don't have to wait to decide what launch vehicle and when until another 2 or 3 years. So we can move ahead on the development of the orbiter and the lander, and then over the next 2-3 years, as we know the availability of these launch vehicles, their cost, then we can, working with NASA, I'm sure they'll come to you with what's the right, combination of SLS and, and the traditional launch vehicle. So let me close by a quote that I would like to mention from President Teddy Roosevelt, because such a program is challenging. We're going to have successes, we're going to have failures. But let me repeat, and I'm quoting what he said, "It is far better to do mighty things, to win glorious triumph, even though checkered by failure, than to rank with these timid spirits that know neither victory nor defeat." The exploration of the ocean world is one of the mightiest things that our country can do, and we sure are not known to be timid. Thank you very much.
Thank you, Dr. Elachi. Dr. Lunine?
Thank you, Chairman Culberson, Ranking Member Honda, and members of the subcommittee. It's a wonderful opportunity to present my views on the search for life in the ocean worlds of our solar system, but I'm going to keep my remarks brief because the chairman and the ranking member so well summarized why it is we want to go to each of these worlds. But I do want to say that I personally feel passionately patriotic and proud of what our nation has accomplished in the exploration of the solar system. And I feel humbled personally to be a scientist participating in one of the greatest space odysseys ever undertaken, the Cassini mission to Saturn. This is an extraordinary voyage of discovery with which I've been involved essentially in the planning stages when I was a graduate student up to today. And this mission truly exemplifies the remarkable things that this nation can do, and in particular the remarkable things that the Jet Propulsion Laboratory, ably led by my friend and colleague, have been able to do over the years. These are historic missions, and their impact is historic as well. So both Cassini and its antecedent at Jupiter, the Galileo orbiter, have provided incontrovertible evidence that there are saltwater oceans underneath the icy surfaces of 3 moons of the outer solar system, Europa at Jupiter, Enceladus and Titan at Saturn. And on Titan, Cassini has discovered vast seas of hydrocarbon liquids, methane and ethane, essentially hundreds of times more hydrocarbons than the known gas reserves on the planet Earth. Now, Dr. Elachi has talked already at length about Europa, and so I'm not going to discuss that, but I want to make sure that everyone understands that I, too, find the exploration of Europa and the search for life there a top priority. So I'm happy to answer questions about Europa. But I'll press on to Titan, which is larger than the planet Mercury, the only moon to host a dense atmosphere of nitrogen and methane. Cassini and the European lander that it carried with it, Huygens, have revealed a methane hydrologic cycle with clouds, rain, river valleys, vast seas, all involving methane and all going on in an unimaginably frigid environment. And yet Titan's surface has all of the formal requirements for life: abundant organics, liquids, and sources of energy. But because that liquid is not water, we have to ask the question, is this really a place that we want to go look for life? It would have to be very exotic life. But a 2007 National Research Council study, in fact, said that we should. And it said that Titan is a test for the universality of life as an outcome of cosmic evolution. So if we're going to look for life in those seas, the best way to do that is to land a capsule, float across the surface. That would be the first maritime exploration of an alien sea, which in and of itself would be an extraordinary adventure. Now let me move on to Enceladus. Enceladus has not surprised scientists. It's completely shocked us. It's a very small moon, and yet it has a plume of material pouring out into space from a series of fractures in its south polar region. And it was Cassini that discovered this plume of icy grains and vapor, and then flew through that plume 7 times, surviving each time. Thanks to the prodigious capability of its instruments, its chemical sniffers, Cassini has found not only water, ice, and water vapor, but also organic molecules, salt dissolved in the water, tiny grains of silica, all indicators that inside Enceladus, down in this small liquid water salty ocean, is a hydrothermal system, a place in which water, organics, and minerals are heated together in the kind of chemical stew that many scientists think was the place where life began on Earth 4 billion years ago. And there really is a subsurface ocean. Cassini is so powerful in terms of its scientific capability, it's detected the presence of the ocean in 2 completely independent ways. And so if you look at all the requirements for terrestrial type life, liquid water, organics, minerals, energy, chemical gradients, Enceladus has it all. And all that stuff is pouring out into space. It's not hidden beneath the surface. And so, as far as we understand it today, Enceladus provides us with the most straightforward way to look for signs of life, given the compelling evidence that much of the gas in the grains are being expelled from the interior ocean. So let me make this very clear. To sample the plume of Enceladus is to sample the ocean beneath the surface. So merely flying through the plume as Cassini has done, but with instrumentation more modern than Cassini's, is sufficient to search for signs of life. And this can be done for well below the cost of a flagship mission, and it can be done with instruments available for flight today. So let me summarize by saying that discovering life on or within the ocean worlds of our own solar system may provide unexpected and as yet hard to predict practical benefits, something that Carl Sagan pointed out many decades ago. But more profoundly, it will inevitably direct our attention to the Milky Way galaxy beyond the confines of our own planetary system. If life can begin 2 or 3 or 4 times in our own solar system, then the number of planets in the galaxy as a whole that harbor life must be enormously great. And then how could we resist taking the leap beyond our solar system to explore the vast spaces between the stars for life there? Thank you very much for the opportunity to talk to you today.
Thank you, Dr. Lunine, Dr. Elachi, and I know my colleagues have questions.
Background music after that?
It's
Yeah.
it is extraordinary, isn't it? We have the Congress, both Republicans and Democrats alike, strongly support NASA and its mission. It's one of the most gratifying things we get to do is to help you seek out new life and discover these incredible new worlds. And I have, in our bill this year, we funded the NASA has the largest appropriation they've ever received since the start of the agency in 1958. And we've got planetary science funded at a level of $1.63 billion this year. What level of funding, in your opinion, Dr. Elachi, will be necessary in the 17 bill to make sure that we stay on track, that the planetary science community has the resources they need to achieve the objectives of the Kittle Survey, both for this flagship mission to Europa and the New Frontiers and Discovery class missions?
Well, I think that's a better question to ask for NASA, for this thing. But clearly, it all depends on when do you want these missions to happen. So from my experience, based on Cassini and other missions, typically it takes us 6 to 7 years after the selection of the payload to actually be ready to be on the launch pad. And in the case of the orbiter or the multi-flyby, the instrument was selected a year ago. So we can add 6 to 7 years to it. In the case of the lander, it heavily will depend on the payload. So a critical element, before we can tell you really the detailed cost.
But we're on the right track. This funding level that we're on now has got you've got what you need so far.
Well, clearly, depending when you want. If you want to launch in the early 20s, the present level is not sufficient, to do that. I'm sure we can provide you with a more accurate, number for it, but I think it's appropriate for NASA. Now, for the total cost of the mission, as you know, it's NASA makes a commitment when we do the ADPC, which is a decision that it makes when we start in the implementation. And those will be coming up in the next couple of years. But we can use as a reference, the Cassini mission or the Mars 2020 mission, because those are well-known missions of similar class to what we're talking about.
When Neil Armstrong's first set foot on the moon, that's an extraordinarily important and historic milestone. But the discovery of life on another world, I think, will be another one of those transformational moments in human history that, when that occurs, will encourage the it'll galvanize the country and the world, and certainly encourage the nation to take NASA even further, funding levels that you will need to make sure the American space program is the best in the world. And that's actually another reason I've been so enthusiastic about this mission, is it holds the greatest promise for that first discovery of life on another world, which will then enable the entire country to get behind NASA with the funding levels that you need to do what's necessary to keep the American space program the best in the world. But for this mission to succeed, Dr. Elachi, I wanted to ask you about the launch vehicle. What do you talk to us, if you could, about the importance of using SLS for the Europa mission, and can you talk to us a little bit about whether or not it will require one or two SLS missions, for example, one for the orbiter and one for the lander? Can you talk to us a little bit about
Sure. No, I'll be glad to address that. As I mentioned earlier, with the EALVs, the present launch vehicle, it takes at least 7.5 years, to get to Jupiter, because we have to do a series of flybys. With an SLS, we can do it in 2.5 years. And that would lead to, even if the SLS might be more expensive, but it leads to saving of 5 years of mission operation. So the trade is not, need to be looked at. Now, the plan now, we're looking at having the orbiter and the lander as two separate spacecraft. And there are different ways you can launch them. You can put them both on one SLS, but because that will lead to a heavy payload, that still will require to do one flyby, by Earth. So that will take us, then it will add 1 or 2 years to the mission. Or you can launch them two separately, on two SLS. And then in that case, you can get much faster to Jupiter. So over the next few months, at the request of NASA, we're going to look at all these different combinations, one SLS, two SLS, EALVs, and provide NASA technically how long it will take us to get there and when will we be able to land, but also cost-wise, what are the trade. So we should be able to get back to you, over the next few months with that trade. Now, as I said earlier, we don't need to decide today what launch that will, what kind of configuration. We can wait about 2 years before we do that. But no question, the SLS or any equivalent, if there is a Falcon 9 Heavy, will revolutionize how we explore the outer solar system. It will make a huge difference when you send a mission to wait 7 years, then analyze the data before you plan the next one, versus all what you have to wait is 2 years. So no question, the SLS will be a game changer in this area.
Thank you. They're going to call votes between about 11:20, I understand, and 11:30. So I want to move on to my... Oh, excuse me, 11:30, 11:50. So we do have a little more time. Mr. Honda.
Thank you, Mr. Chair. Dr. Elachi, what are the primary science goals of the Europa orbiter and related missions? And is astrobiology and biomapping part of the stated NASA objectives?
Let me briefly answer it, but my colleague here is smarter than me when it comes to astrobiology. The orbiter, which has the payload selected already, will do very high-resolution mapping of the surface, will look at the composition at the surface with spectrometers, and will allow us to sound through the ice so we can determine how thick that ice. Mm-hmm. And with the gravity measurement, we'll be able to determine the characteristic of the ocean, how thick that ocean is. So it provides us all the ingredients that are needed to start planning for the next step with the measurements that the lander will get by making in situ measurement of astrobiological components as well as the characteristic of that ice. So let me, if permission, let me turn it to Jonathan. He's smarter than me in that area.
Well, I'm not sure I would agree with that statement, but the Europa flyby mission is very, very well instrumented to address astrobiology goals. And in fact, within the organization of the mission itself, we have what's called a habitability working group to look at how these instruments can address those goals. And so there is an instrument that will look for organics on the surface that might have been deposited from the interior. We must understand whether Europa has carbon-bearing compounds, organic molecules. We don't know that today, and that's a key ingredient for habitability because that's what life as we know it is made of. And there are two instruments, mass spectrometers, that will actually sample Europa material directly on the flyby spacecraft. If there's a plume, they'll sample material in the plume. If not, they will actually sample material that's been deposited on the surface that gets bombarded by micrometeoroids and is then lofted into the atmosphere. And both of those instruments can measure the composition, look for organics as well, and even possibly look for clues that there might be a hydrothermal system in Europa's interior. So I think we're going to get a great deal of information on the habitability of Europa just from the flybys themselves, and then a lander, of course, would provide in situ information to add to that.
Okay, so this may be the same question in a different way, though. So if life detection is one of these goals, how will this be accomplished by a potential Europa orbiter mission without a secondary mission or landers? And how likely are we to learn something from an orbiter mission that will affect what we would want to know with a lander, both guide where we would want to land and with what type of craft as well as the instruments to put on the lander? And then I understand for decades NASA and JPL have successfully explored planets and their moons through a three-step strategy of flyby, followed by an orbiter, and then followed by a lander. I've heard this described in your testimony. Each step on this journey builds on the knowledge gained through previous missions, which you've explained. And this is designed to maximize the science return at each step while minimizing scientific and technical risks to spacecraft, landers, and rovers. With respect to a Europa mission concept involving a lander, what provides the confidence that we would know enough about the Europa surface to ensure that a lander will be placed on a scientifically compelling and safe site on the icy surface?
Again,
I know it's a lot of information, but I was just trying to put it all together so I can conceptually understand.
Okay. First question.
Okay. No, I think our strategy is the orbiter will get to Jupiter before the lander. Mm-hmm. And it will survey the area, image it at very high resolution, identify the area of interest. And the lander, even if they are launched on the same launch vehicle,
right,
will put the lander at a high altitude orbit to protect it from radiation, wait until the orbiter maps the surface, then we'll zoom in and come down. Nothing will replace in situ measurement. There will be always uncertainty until you actually grab some of that ice and measure it in a mass spectrometer. The additional thing we need to be thinking about is we need to learn how to land on Europa for the ultimate mission where actually we have to drill. So this lander that we are talking about will have a great scientific value, but also it will have the value of learning how to land. That's what we did on Mars. First we landed Pathfinder, then we landed, and we drove a little bit, then Spirit and Opportunity, and then Curiosity. So I think we have enough information that we don't have to wait for a mission to be completed before you get to the next mission. We have worked a strategy that you can do it on a much faster, time. So let me turn it.
And then just very briefly, Congressman Honda, there's a very important distinction that has to be made between habitability and looking for life itself. And in the case of Europa, we are still at the stage of determining whether Europa is habitable. The saltwater ocean indeed seems to be there, but what we still don't know yet is whether there are organic molecules. In Europa, it's possible that there were never any, or they've all been essentially exhaled into space in some way. So that's crucial. And then the whole issue of whether there are hydrothermal systems at the base of the ocean to generate the gradients in energy that life would need. We need the clues, again, from the minerals that might be coming out of plumes that might be deposited on the surface. So the mission, as it's constructed today, will really address the habitability of Europa. And if those indicators are positive, then going after the question of whether life actually exists there becomes the primary goal at that point.
Thank you. Jolly.
I see they rang for votes. I'll be very brief. I know this is a priority of the chairman, so I want you to have as much time as possible. Chairman's been very helpful to me in the Gulf of Mexico and making sure we know how to count fish, so I'm happy to support your initiatives here in space. My only question is, in these oceans you're finding, are there any red snapper in them? But look, we have the right chairman, the right ranking member on these issues right now. I'm excited to support what you're doing, so thank you all for being here today. Appreciate it.
Mr. Fattah.
Thank you. So it's with mixed emotions. Your retirement is both well-deserved, but your leadership has been extraordinary. And I visited the Jet Propulsion Laboratory. I was on the floor with you when the Mars rover landed on the surface, and it was an extraordinary success for the Jet Propulsion Laboratory, for NASA, for our country, and for science worldwide. So I want to congratulate you on all your hard work and your success at the laboratory, and wish you well in your next endeavor. I'm sure there's a second act or third act here. But I want to ask you a couple questions. Given the fact that you're stepping off the stage, if you could give the committee some reflection on, we at one point had a lot of back and forth. It was pretty lonely in advocating for commercial crew and commercial cargo and the space technology portion of the NASA budget, because there was a lot of buy-in to what we might call the old NASA, right? And so there was this big tug-of-war that's now been settled. And we have a robust, competitive, I think, commercial crew operation. This is talking about, and so it really puts NASA and the Jet Propulsion Laboratory in a position to focus in on exploration. So if you could give us a few minutes on your thoughts about where we are in terms of the decision package around these issues, that would be helpful.
Okay, sure, I'll be glad to do that. Let me first start by saying I'm retiring from being the JPL director, but I will be professor at Caltech, which I am present. So I will stay engaged. I mean, I spent 40 years on this amazing quest of exploration. So I will continue to be engaged in that one. Now, on your second one, I think it's like every time NASA develop a capability, we need to turn it over to the commercial sector so they can make a business, out of it. That has happened on telecom satellites, GPS, and NASA to be exploring the next frontier. That's what our agency should be doing, and I think that's what our agency is focusing on doing. So I think the commercial sector, particularly in the launch area, should be able to support that activity so we can spend our effort either on more capable launch vehicle like the SLS or exploring mission like Europa. Now, talking about a little bit on technology, I want to add one statement. When we landed Curiosity, of course I was proud of the landing of Curiosity. We're delighted that you and your daughter were there. But what I was particularly proud of is all over it was written made in the USA. Because almost every piece of it, we don't import this stuff. We actually build it in the United States. So every dollar we spend in our space program is spent in the United States, for jobs, for developing technology, and so on. And the critical element was the investment in technology, in enhancing our capability to do these amazing things. These things don't happen. And no commercial sector will invest in technology which is needed 10, 15 years from now. And that's what NASA should be doing. So I'm a strong advocate of the technology program, for NASA, because that's what enables the future for us. And at the same time, to turn over the things that the commercial sector can do to the commercial sector to do that. And I think that's a NASA strategy that is being advocated today.
Well, thank you, and I want to thank the chairman for his extraordinary leadership, not just in terms of Europa, because he's been, I think, a robust supporter of our space effort, and we again are thankful that in the omnibus that we were able to get a very good number on commercial crew and space technology, technology, and I brought my daughter out there because we wanted to. She's interested in Caltech, so she's 17. She's honor roll, 99 percentile. We, somewhere between the University of Texas and Caltech. You know, who knows? Thank you. Thank you.
We've got 2 votes, and Mr. Honda would like to come back. I'd like to come back, so if we could recess briefly, and we'll take these votes, and then we'll come back and have a few more questions. So the committee will stand in recess briefly. Thank you. All right, thank you, Mr. Honda. The hearing will come back to order. We've finished up our votes, and I appreciate very much your patience with us taking a brief recess while we finished up on the House floor. I wonder if I could to ask Dr. Elachi in particular, of course, as you know, the fiscal year 2016 Appropriations Act directed NASA to launch a mission to Europa with a lander in order to confirm the presence of organics. If I could ask both of you, first of all, how essential is it that we land on the surface in order to confirm the presence of organics?
I think in order to make sure we have confirmation, you really need to make direct measurements and use it in a mass spectrometer to do that.
On the surface?
On the surface. We don't know first if there are plumes. So the only way to make sure we do that is to land on the surface and make direct measurement, take samples and make direct measurement, because any other way you are going to be still uncertain, doing that. So that's a direct important thing. The other part I want to emphasize is also you need to learn how to land on the surface of Europa for the longer term. And it is within our capability, to do that. So clearly a lander on the surface, in my mind, is a necessity in understanding the oceans on Europa.
Dr. Lunine?
So I've participated in some of the discussions on the lander payload, and it's a very carefully selected payload that's designed to give us the essential information we really need to go the next step to look for life, if in fact everything turns out to be positive. And so one of the things that's essential about the lander is the ability to sample deposits that are on the surface that may be partially covered up, that may not in fact be exposed to the orbiter remote sensing. And so, we want to have the opportunity to use both the flyby spacecraft and the lander together to select the right landing site, to put the lander there, and then to sample the materials in situ. And we may get lucky with that in situ analysis. I mean, we may actually find evidence that the organic molecules are being modified in some way by biological processes.
So you'd agree the only way to be certain is to land on the surface and actually test the ice deposits on the surface. That's the only way to be sure.
That's the only way to be sure, but it's got to be done in concert with that flyby spacecraft, because we need to understand, what the nature of the surface is at a level of resolution good enough that a lander can be put in the right place.
Actually, let me add one thing. When you look at the decadal and what are the science that they listed, we did generate a table which looked at what can the orbiter do. And the orbiter can do the majority of the science, but cannot do and answer directly the question of the organic on the surface. So that was a gap that the orbiter could not do. And that's why the lander is critical, for this mission.
And that's why, of course, as our bill states, the goal of this mission is to achieve the scientific objectives of the decadal survey, which, as you've just confirmed for the record, has to include a lander if we're going to answer that essential and most exciting question of all, is there life on other worlds? And if I could, Dr. Elachi, ask about when does NASA intend to solicit instruments for the landers with an announcement of opportunity in fiscal 2016?
Okay, basically, again, that's a question NASA will need to answer. But NASA, to their credit, they just sent an email to the broad science community inviting people to submit, that they would like to work on this science definition team. And they stated in that letter that this is for about 3 months, where they will work with JPL, with NASA on defining the payload. So they should be able to get that work done, I would say, by early summer, time frame. And then NASA will have to go through its process. So that's something that you need to address with NASA, of when will they issue the announcement of opportunity for the instrument. In my mind, the earlier is the better, because the payload is the key driver for developing the lander, because we can do a certain amount of work, but until we know what instrument you need, how much samples you need to get, what volume you need, it's hard to do the detail, design. So it's critical to have the AO and the selection of the payload in the most expeditious way.
Well, we will push NASA to make sure they get this done as rapidly as possible. And I also hope that we'll see at least 2 ways to verify the organics with the mass spectrometer and the Raman on the same lander. Because if we're going to go all this way and make this exciting mission, make sure that we actually are detecting organics, it makes sense to double check it, doesn't it?
Yeah, I agree with you. And the design, the very preliminary design that we presented to NASA will accommodate at least 2 in situ instruments, will accommodate kind of a seismometer to look at any vibration, and will accommodate imaging. Now, if NASA decide and the science group decide that they need more instrument, we can do that. But that makes the lander more and more complex of doing. So that's a trade
Yes.
which have to be done with the science community of what's the optimum payload which enable to answer the question, but also can be done with a reasonable risk.
And the payload will be comparable to that which landed on Spirit and Opportunity on Mars in terms of the weight and size?
I don't know about the weight and size, but at least one of the instruments, the Raman spectrometer, will be based on heritage, from Spirit, not Spirit and Opportunity, but from Curiosity.
Mm-hmm.
We have a Raman spectrometer and on Mars 2020. But I'll let Jonathan maybe.
Well, and I just wanted to add that you mentioned that having a mass spectrometer and Raman allows you to have backup and have 2 ways of detecting the organics. The Raman also gives you some information on structure that is important that you may not get from the mass spectrometer. And understanding aspects of the structure of the organics is important in telling how fresh they are and where they come from. Were they part of a biological process of some kind, or were they not?
I'll have a couple of follow-ups. I want to recognize my good friend, Mr. Honda.
Thank you, Mr. Chairman. Through this discussion, I'm sort of developing a picture in my mind that one of the things we want to do is to be able to understand through various techniques of the possibility of life, whether it's through indirect or direct techniques, and also, and prior to landing on the surface, it seems to me that we need to know how firm or what the structure is so that it'll sustain a landing. So, and then also, inserting ourselves on a planet, I'm a little concerned about contamination too. So, could you talk a little bit about kinds of testing that needs to be done? And I know that you talked about handedness. That seems to be important. The issue of habitability through the indirect detection of processes that you want to go through in order to see what's down there, and the types of techniques. I think I heard fly-through plumes, things like that. Are these all necessary processes in order to determine whether the surface is can enable a landing of a craft on the surface of the planet?
Well, let me talk about the life tests, and then I'll ask Dr. Elachi to talk about the questions of certifying the surface for a safe landing, which is really a different subject. So I think that the flyby spacecraft will be able to pretty quickly tell us the coarse essentials about habitability. Does it see that there are deposits of organics on the surface? It's not going to be able to tell us in detail what the organics are, but it will tell us whether there are carbon-bearing molecules near the fractures, for example, which we don't know, and Galileo was not able to tell us. Galileo was able to tell us that the ocean is there and salty. There are indications of salt deposits on the surface, but again, Galileo couldn't tell us which kinds of salts. So we really, for Europa, have this rudimentary information that I think the flyby spacecraft will very quickly develop into a full profile of how habitable Europa really is. And then, of course, the next step, both from the flyby spacecraft and from a lander, is to determine, potentially whether there's biological activity. There are a number of ways to do that. There are, of course, direct detection of organisms requires potentially very elaborate instrumentation. It's better to analyze if there are fresh organics on the surface to look for evidence of a preponderance of left-handed and a deficit of right-handed, or vice versa, organic molecules if there are amino acids. And in general, yes?
Could you explain the difference and the importance of?
Yes, so life, of course, life on Earth, it's all biochemically the same. We have no other example of life. And the amino acids that life uses, with only small exceptions, all have a particular orientation or handedness, the way that the carbon atoms are attached to the molecules themselves. And that actually allows the amino acids, when they are arrayed in a chain to make a protein, to actually allow that chain to fold properly to make a protein. If you had a mixture of the left-handed and the mirror form, if you had a random assortment, when they're arrayed on a chain, you don't get a protein. Now, it doesn't matter if it's left-handed or right-handed. It could be all right-handed or it could be all left-handed, but it's got to be one or the other. And so identifying that, first of all, if there are amino acids, and secondly, are they all left or all right, is one very powerful example of a life test, a test for life. That's chirality, exactly. Do you want to talk about the surface?
I think on the question of the safety of landing on the surface, as I mentioned earlier, the orbiter is going to be taking very high-resolution imaging of the surface. Now remember, Europa is the size of our moon, so it's a big satellite. So we'll be taking the images to decide what area are scientifically valuable and safe to land. In addition to that, as the lander is coming down, it will have the capability of actually taking pictures as it's coming down and move to make sure it's in a safe place. That technique we're going to be demonstrating on March 2020, so we'll have it well understood. And the third thing on top of that, the way we land, we're putting the lander inside a pyramid, similar to what we did with Spirit and Opportunity and Pathfinder. So even if it lands on the side or there is a rock next to it, it can unfurl and right itself up. So these are 3 steps which will assure us that we'll be able to land safely on the surface.
Through the chair, the reason I asked about the handedness and contamination connected to landing or flyby or fly-through, whatever the term is, I was trying to figure out if you can determine the amino acid handedness through a fly-through so that you have that information prior to landing. I mean, is there ways that you can do that? Or is that one of the things?
Well, the only way to do that would be if Europa had a plume. If it's got a plume of material where you have fresh material pouring out of the ocean that can be sampled by instruments, potentially you could do that. However, the Europa flyby spacecraft doesn't actually have a device for measuring chirality, and that's actually
Measuring
a
what?
fairly complex type of instrument.
Measure
To
what?
measure the left, excuse me, sorry, to measure left versus right-handed. That's not part of the payload. It can detect molecules, but it can't tell you what the structure is in terms of left or right-handed. And that's a type of instrument that requires some development, probably should be on a lander.
Thank you. You'd have to make that measurement on the surface, on the spot, in order to be able to determine the left or right-handedness.
In fresh material that has not been damaged by the radiation field.
Right. And plus, I also understand from the briefings that I've been given that speed of flyby is so high that any organic material that might be in that plume would be disintegrated by the, so you really, another reason to land on the surface is the, any organics in that plume, when you fly through it, would probably disintegrate it, as I recall. The speed is so
Mr.
high.
Chairman, not having that experience of hearing, is that plume created naturally, or is that induced through, creating a plume ourselves?
No, the plume is created naturally. It's like Enceladus. The ocean is venting through cracks in the ice into the lower pressure, because it's essentially a vacuum, and it just is. We've seen it in Enceladus, detected a plume on the on Europa once or twice from Hubble.
Yeah, let me mention one thing. First, on Enceladus, we see the plumes coming regularly. So there you have confidence. And Jonathan has been thinking of how do you measure that. On Europa, we have not confirmed that there are plumes. Now, you could think, well, I could impact the surface and create the plume. But when you impact the surface, you have to do it at extremely high speed. And that could create a lot of damage for whatever is on the surface. I mean, the damaging the molecule you are trying to measure, because you are hitting it with a bullet to do that. So I'm not sure that's a good or wise technique to do that. And we don't know if naturally there are plumes. So clearly the best approach and the safest approach is to put a lander, a soft lander, on the surface and make that, and drill below the surface and make that measurement.
In the pyramid you're discussing, it would land similar to Spirit and Opportunity. There'd be airbags around the
Well, we're
pyramid.
not sure we will put airbags, but it will be very similar. The shape will be very similar. And we are in the early stage of looking at these techniques. By bringing it with a sky crane and being able to have control before we land, that addresses significantly the risk issue.
Could you talk a little bit about what we know about the ice? The surface is, it's a free-floating ice shell. Not sure how thick, but the age.
Okay. Yeah, so this is a very interesting question. It is a very young surface. There's only one really old large crater on one part of Europa. And there are places on the surface where the crust may be as thin as a few hundred meters, perhaps, places where you see these cycloidal ridges that appear to be a response to the tidal pull, the tidal stresses as Europa goes around Jupiter. Those are the places where the crust may be very thin. There are other places, for example, where this one crater, Puil, is located, where the crust appears to be thick. It may be 10 or 20 kilometers thick. So you have to imagine that this, as you said, Mr. Chairman, this free-floating ice shell just has a variation in thickness as you go around Europa. And one of the important goals of this mission is to determine, the ice thickness in various places and determine where the ocean is really closest to the surface.
And if the surface is that young, it obviously implies that it's being continually replenished and that that ice is diving down into the ocean and coming back up. And because of the intense radiation, I think I've read that the hydrogen atoms are being stripped away from the H2O, which means it's oxygen-enriched ice going down into the ocean and releasing that oxygen. So it's plausible that that ocean has been oxygenated for billions of years?
Yeah, this is a very interesting aspect of Europa, that this may in fact be a primary source of energy for life, are these oxygen atoms that have, as you said, the hydrogen's been stripped, and then these very oxidized species, peroxides and so on, are being introduced into the ocean. By one estimate in one paper I read, there may be as much energy from that as we have in certain oxygen-rich aerobic systems in the Earth's oceans. Now, you wouldn't want to try to form life in that environment, right? Because oxygen is a destroyer of organic compounds. So we would also like to know whether there are places in the deep ocean of Europa which are not exposed to quite that much oxygen, or at least were not in the past, because in order to actually build these organic molecules before life itself began, you would have had a relatively oxygen-free environment.
I also understand from talking to Dr. Robert Ballard that these mid-ocean ridges, which are not visible here, the largest volcanic system on the Earth, the 40,000-mile-long mid-ocean ridge, that Dr. Ballard told us, Mike, that for years geologists couldn't figure out the chemistry of the Earth's ocean. They didn't understand why it had the mixture of chemicals that it did, that the rivers flowing into the ocean, you couldn't account for the chemistry of the ocean just based on rivers until they discovered these mid-ocean ridges. And Dr. Ballard points out that the entire volume of Earth's oceans circulate through those mid-ocean ridges every few million years. he thinks maybe 4 to 6 million years. And that injects a tremendous amount of chemicals into the Earth's oceans, which once they did that calculation, it matched perfectly, and it explained why the Earth's oceans have the level of salt and other chemical elements within it. And clearly, wouldn't you say that's a reasonable analogy to what we see in Europa with the silicate? You're detecting silica in the plumes on Enceladus. Almost certainly, I mean, you've got a rocky bottom to the oceans of Europa. So is it reasonable to assume that you've got similar circulation of the salt water on Europa going through those volcanic black smokers? We'll probably have black smokers on the bottom of the oceans of Europa, as we see on Earth?
Yeah, that's a very interesting question for Europa, and the fact that it's a large body that has a large rock core makes it likely that there is some sort of hydrothermal circulation of water through the hot rock. Now, whether it's a black smoker or some of these other types of what are called off-axis hydrothermal systems that are a little bit cooler, is not really clear, and one of the goals of this mission, by determining what are the kinds of salts that have been deposited from the interior and what other kinds of mineral evidence might there be on the surface, we might be able to know what type of hydrothermal system is present. On Enceladus, what's interesting is that the Cassini data from the mass spectrometers are good enough that the pH, the acidity of the ocean, has been estimated from those data, and as well the temperature in a very sort of crude way from these silica particles that have been sampled by Cassini. And those data suggest that there is a hydrothermal system at the base of the Enceladus Ocean, and it's more like the low-temperature hydrothermal systems that are off the mid-ocean ridge, off of the axis. There's one called Lost City, for example, and it has a temperature of about 50 Celsius, and it has a high pH, as Enceladus does. And it's a different kind of chemistry, and that's what looks like might be happening at the base of the Enceladus Ocean. So it'll be very intriguing to see what is happening in the Europa Ocean, whether it's similar to that or more similar to the higher temperature black smokers.
I don't want to intrude. Mr. Honda.
Okay. Leaving the planet, coming back to Earth, in your independent opinion, what is the estimated life cycle cost of the Europa orbiter mission, both with and without a proposed lander? And how soon do you believe a Europa orbiter mission could be launched, and what assumptions must be made to support that launch date? And how long would inclusion of a lander delay arrival of a spacecraft of Europa? I think you alluded to that, including development of time and transit time.
Well, let me answer it first on the technical side. On the technical side, the two are complementary. It won't impact. We can move ahead with the orbiter on its present schedule. At the end, the key driver is going to be the funding for it. And that's what we are developing now to provide NASA for the funding profile that is needed based on the direction which came from your committee about when to do the launch. So we will be providing that to NASA. Now, originally, maybe your concern comes, originally we were thinking of having the lander attached to the orbiter, and therefore the orbiter will have to wait for the lander to be finished. That's not our plan now. We found that technically that's not a good approach. So we'll have the orbiter and the lander as two separate spacecraft. And as I mentioned earlier, 3 years from now, we can decide, do we launch them together or do we launch them separately? Now, for Jupiter, fortunately, we can go to Jupiter roughly every year. You know, in actuality, it's about 13 months. So you can plan it depending on the readiness of the orbiter, the readiness of the lander, the availability of the launch vehicle. But you have a shot every year to actually do that if we decide to do them separate of the two. And so we are doing all these assessments. Should they be launched together or should we launch separate? But they will be developed separately. So it won't impact the orbiter schedule.
The development time and transit time, it's dependent on what our decisions are then.
Sorry?
The transit time and development time is dependent upon our decisions then.
Well, the time of development is once you select the payload, you need roughly about 6 to 7 years to be at the launch pad. That's from our experience on Mars 2020, Cassini, Galileo, all these missions. And if you try to do it much shorter, that's not wise because you are taking big risk. If you wait longer than that much, that's not efficient because you build your team and all the activity. You know, if you start stretching it, that's not the way to do things. So really the driver is, the trigger point is, in my mind, the selection of the payload, and then you can add 6 to 7 years, assuming funding are available, 6 to 7 years to be ready to be on the launch pad.
The chairman would be here more than 6 or 7 years, right? Thank you, Mr. Chairman.
Just to wrap up on Europa, I want to make sure I understand that you've got a oxygenated ocean, this obvious evidence of a lot of heat, probably circulation through those volcanic ridges. The ice would also protect that ocean from asteroid impact and radiation. So a very stable and secure environment for potentially life to not only begin, but to then be sheltered for essentially the life of the moon. Is that accurate?
As far as everything we know today, yes, that's right. And what we don't know today is how much carbon and nitrogen-bearing material is in Europa, and we really need to know that. And if I may, Mr. Chairman, the first proposal that I wrote for an instrument on a Europa mission was in 1999, and so some of us have been waiting 17 years for a mission to get going, and that was, of course, just 2 years after Galileo discovered evidence for the ocean through its magnetometers. So, you know, I have to say that it's past time to get to Europa, and the sooner that we can get there to explore this incredibly fascinating moon that may well hold life, the better.
Yeah, let me add to it, Jonathan. So that reflects that the science community have been thinking. So it's well thought of what need to be measured. And that's why, you know, the decadal indicated things and the lower measurement, which as of now can only be done with a lander. The other question on the radiation, I'm not an expert, but I ask people at GPL, all what you have to do is to go to just a few centimeters below the ice, and you are somewhat safe from radiation. That's why Jonathan emphasized that when we take the samples, we need to drill a few centimeters, a few tens of centimeters, so you get fresh ice coming from which is not bombarded by the radiation. So you don't have to drill too far to actually find what we're looking for.
And I want to stress, too, of course, for the record, that this is obviously a keen interest of the committee, of mine, but it is the top priority of the decadal survey. This is something that we're pursuing, Mr. Honda, and the subcommittee is supporting, because this is the consensus of the scientific community in the decadal survey, correct? Yes. That we need to go to
Yes,
Europa.
that's correct, absolutely.
And
Yeah, so that,
I want to also, if I could, because the other purpose of this hearing today, and we'll wrap up here in a few minutes, but I want to lay the foundation for the future. The idea of this hearing was to talk about the exploration of these ocean worlds as a great opportunity to discover life, perhaps in our own backyard. Talk to us about, if you could, as you mentioned, the oceans of Enceladus. That's a free-floating ice shell as well?
Yes, it is a free-floating ice shell. It's thicker. It's about 30 kilometers thick as far as we can tell. So we really are depending on the plume sampling material coming out through the fractures into space in order to learn more about that ocean's habitability and the possibility that life is present.
And the water, go ahead, sorry, Dr.
no, I just want to mention, you probably know it, but to the credit of NASA, they added Enceladus and Titan to the potential targets for the New Frontier program. As you know, in your bill, you said to look at an ocean program which involved flagship mission, New Frontier, and Discovery. So NASA did add Titan and Enceladus as potential candidates for the New Frontier mission. I think Discovery is a little bit harder because the outer solar system is pretty far away,
Right.
you know, to do that.
Right. And those, of course, would also be prime candidates for use on the, for launch on the SLS.
No,
They're smaller spacecraft, but again, to get there rapidly, you would need the SLS?
Again, I mean, the biggest benefit of the SLS is the speed and that it can carry more mass. So depending what, I mean, we're in the process of thinking of ideas, for the Titan mission and the Enceladus, and Jonathan is a key player in both of them. Depending what the scientists come up with, that will lead to what's the right launch vehicle.
How deep is the ocean on Titan, do you think?
So
Or is it a sea?
well, there is a liquid water ocean on Titan, and in fact, the Cassini evidence is that it's also a decoupled shell, but it's very deep. It's at least 60 kilometers, and it may be more like 100 kilometers below the surface. So of all three of those bodies, sampling material from the Titan subsurface water ocean is going to be the most difficult target. But there are also these hydrocarbon seas on the surface, and they may be an interesting target, and they're exposed to the atmosphere. You can land on those.
Now, to answer your question, from the Cassini mission, we know those surface oceans, which are made of hydrocarbon, are the size of the Great Lakes. So this is not like a pond, but it's not a Pacific Ocean. But they are very large lakes, and as Jonathan mentioned, the amount of water, or hydrocarbons, which is in them exceed by how much, what's the height? 2 orders of magnitude how much hydrocarbon there is on our planet. So that could be an indicator of some exotic life, a different way of life.
Mr. Honda, dive in anytime.
So I guess I'll close with this questions then. With that discussion, then it sounds like there's that possibility, or have you thought about how we recycle the assets that we're already developing or we will be using? Would that be recyclable and be able to continue to use as we seek out other solar oceans? And I guess the other would be, should we be looking at building smaller fleets of assets so that we can, as we're pursuing this project, we could be thinking about, in a parallel way, building smaller fleets to continue this search for ocean worlds that are out there?
I think what you said is the wisdom of having a program. You need to think of all different elements, to explore Europa, Enceladus, Titan, in a similar way that the Mars program have been thinking about. And it could be a combination of large spacecraft, small spacecraft, boats, drills. So the benefit of having a program is that you can do this kind of thinking that you are mentioning. And also it will allow us to build on one mission, building on the prior mission, both from science but also from hardware, as you develop things. So the same thing on Mars, we build up from Pathfinder to Spirit Opportunities and to Curiosity, then to Mars 2020. And now we're looking at technology such as little helicopters, which can augment, those measurements. And that's enabled because we're thinking it as a program, not one mission at a time and wait until we get the results from it.
Yeah. Okay. Thank you, Mr. Chairman.
If I could also to follow up, because I want to talk a little bit about, before we wrap up, this purpose of this hearing today is to talk about the next step, and it is developing a program like we had with the Mars mission. We've discovered these oceans that exist in the outer solar system. They're undoubtedly probably very common throughout the universe, and it's important that if we're going to discover life, it's going to be in those oceans. Talk first for a moment about, for example, what other moons in the outer solar system do you think could have oceans of water?
Well, we have some evidence for oceans in possibly Callisto, which is one of the other Galilean moons of Jupiter. It might be a very thin ocean. It's somewhat mysterious that it would have one because it seems to be rather cold and dead, but the evidence seems to be there. Triton, which is a moon of Neptune, is very intriguing because it's a large satellite. It was probably captured from the Kuiper belt. It's the size of Pluto. And it has some activity on its surface. When Voyager 2 flew by in 1989, it found that there were these plumes of material coming up that deposit dark streaks across the surface. And while there's some models that say that this is just driven by solar heating of the surface, the fact that we don't see this on Pluto in the same way suggests that maybe this is actually internal activity. that's being expressed at the surface. So Triton is another object that might have an ocean. It's a long way away. Neptune is at the edge of the solar system.
Any of the moons of Uranus indicate any evidence of...
We don't know because, Uranus is tipped on its side, and so when Voyager 2 flew by Uranus, it was essentially a bullseye where the whole satellite orbits were face on, and the whole flyby was quick. It was basically through the target, and the spacecraft had to look very quickly and take a few pictures of each moon. We just don't know very much at all about those moons. And going back at some point and understanding more about them is very interesting. They're large. 4 of them are large. They might have oceans, but we just don't have any evidence.
So the Ocean Moon Exploration Program that we've outlined in our bill will be obviously focused initially, the first mission to Europa, Enceladus, and Titan will be the most immediate and obvious targets. And what we learned from the New Horizons mission to Pluto, large amounts of water in evidence there on Pluto too, isn't it? Frozen, obviously, but
yes. So Pluto,
water on Pluto, and that was unexpected.
yeah, Pluto, just based on its density, was thought to be an ice rock world. What is surprising about it is that there's a lot of geology, that the ice itself seems to have been modified by geologic processes, and there are deposits on the surface of other ices, nitrogen ice, carbon monoxide, methane, which themselves have been flowing across the surface. So it's a very complicated world. The way it looks geologically suggests that maybe, in fact, there is activity inside Pluto that has heated it and melted the water ice. Now, whether that's still going on today, we don't know. But every place we go in the outer solar system is a surprise. There's much more activity, there's much more dynamism, if you will, in these bodies than I think any of us would have predicted.
But the point I wanted to drive at is that everywhere we look, too, out there, there's a lot of water.
Yeah, there's a huge amount of water in the outer solar system.
But just, you created another thought. There's been some question about earth science.
Yeah, clearly, I think as we develop an ocean world program, we should be looking at what can we do also in our oceans. And that's why Dr. Ballard has been involved in some of these activities, because we can learn both ways. By exploring our ocean, you can learn about oceans outside our planet and vice versa. I've been around in this business for like 40 years, and I found many times as we develop things for planetary exploration, the technology and the technique and the knowledge are directly applicable back to our own planet. I started at JPL to work on the Magellan mission, which had an imaging radar on it. Guess what? Now imaging radars are being put in orbit around Earth based on some of that technology that we developed from that. And I have no doubt whatever we do on Europa and the technology we do for submarines or drilling will have some cross benefit with our own ocean and vice versa. Because here we have to develop robotic, small submarines which are capable of making some very advanced measurement. I could see people interested in having dozens of those being put in our own ocean and study what's below the ice in the Arctic and the Antarctic.
Thank you. If I could, having the benefit of your presence here, Dr. Elachi and Dr. Lunine, talk about the far future, because one of the exciting things about this Ocean Worlds Exploration Program is it'll be laying the foundation to develop the next generation of rocket propulsion and to take NASA on to the next level, because when we do discover life in another world, I think that will encourage the public to support the level of funding NASA is going to need. Let me ask first quickly about the work that NASA is doing with the Department of Energy to support radioisotope power systems. Is the level of funding that we have in this year's bill sufficient, and are you satisfied with the work that is being done to to increase the power output and to reduce the mass and size.
To the best of my knowledge, from what I took, I think it's appropriate and the appropriate level. But again, that's a question that headquarters probably can answer. But for our purpose, looking at the near-term mission that we're discussing, I think what's available now and the new production that DOE is doing are satisfactory for that. Now, in the longer term, when we start talking about putting lander to melt our way down below the surface, then we need to, that's why I thought it's important to put some work on the technology of what is needed, so we can assess exactly how would you do it, and will we have enough radioactive material to do that.
That would be the second mission to Europa, would be to get through the ice. This mission will involve some artificial intelligence because of the distances involved. The computers on board will have to make a lot of decisions on their own as they're approaching the surface. Is that?
Absolutely. It has to be all done autonomously because it takes a couple of hours for the signal to go up and down. So everything has to be done autonomously. And that would require the advances that you're talking about.
And that second mission would require a heat source sufficient to melt, for a submersible vehicle to melt through the ice, drop out into that ocean, and then transmit images and information back to the surface to tell us what is beneath that ice, and we hope reach the bottom of that ocean.
Yeah, that is correct. I mean, I don't know about it, depending how thick the ocean is, but
The ice, rather, yeah.
but for that mission, you clearly need you need nuclear capability because it's going to require a long time. The lander that we're talking about now, the precursor lander, that doesn't require a long time. It requires to capture samples, make measurement, and the fact that it's static, it's not a rover. Most of the science can be done in a couple of weeks. Therefore, nuclear material is not needed for the lifetime. It can be run with batteries. But as we head toward drilling down, then I don't see any option other than having nuclear to get enough power, to be able to do that, or energy to be able.
Let me wrap up with talk about W first, and looking out beyond our solar system to identify Earth-like planets around nearby stars, and the coronagraph that you're developing and the Starshade, because it is extraordinarily exciting. And looking out into the future, this W First is essentially a flagship mission in terms of investment. That would be the second that we do the Europa mission, and then the next big mission would probably be W First. Could you tell Mr. Honda and I a little bit about the W First mission and its importance, coupled with Starshade, in identifying and then spectrally analyzing the atmosphere of Earth-like planets around nearby
Let
stars?
me mention on the techniques, and then Jonathan can add the science. W First just passed its phase A, so NASA is proceeding, through the process of doing that. The baseline mission, which was a top priority of the astrophysics community, that baseline mission focuses on two topics: dark energy, dark matter, and on exoplanets. The mission now, the baseline, include a coronagraph inside the spacecraft itself. That allows us to make certain measurement of detecting planet directly by blocking the light from the star and be able to see the planet. And it will detect planet of certain size and distance. We are working on technology, let me emphasize it's technology now, for a potential starshade, which will augment the measurement which are being done by the coronagraph. But that technology, we need a couple of years to demonstrate fully that technology and bring it to a level that the next midterm decadal can assess, the scientific value versus the risk. So we are moving ahead on the technology. But as of now, the baseline W First mission only include a coronagraph inside the spacecraft. Jonathan, do you?
Well, I would only add that, of course, the opportunity to be able to determine the composition of the atmospheres of Earth-sized planets around other stars is the ultimate goal. And in a way, this has already started, because with Hubble and with Spitzer, it's been possible to determine the atmospheric composition of large planets, giant planets, using the transit technique. And James Webb Space Telescope will extend that down to super-Earths, objects that are 2 or maybe 3 times the size of our own Earth. That will tell us a lot already about whether these super-Earths are like our own Earth in terms of atmospheric composition, or perhaps are more like Uranus and Neptune, small versions of those planets. Clearly beyond that, if we want to be able to determine whether there really are habitable Earths the size of our own planet, we'll have to take the next step, and that would have to be done beyond JWST, maybe with W first, maybe with something else.
But you would be able to, with WFIRST, the coronagraph that you already are developing, to be able to directly image or be able to pick up the light of these exoplanets and spectrographically analyze their atmospheres. You could detect, and please for the record, I just want to confirm, the smoking gun for life would be methane, oxygen, together?
Yeah, that would be the smoking gun, but because I'm not involved in W first, I should ask Dr. Elachi to describe the
Could
capability.
WFIRST do that for us, Dr. Elachi, to
Well,
determine?
my understanding, and again, you might want to do a hearing on W first because I'm not there. My understanding is the coronagraph will allow you to image planet separate so yes, separate the light coming from the planet. Mostly for planet larger than Earth, but with the coronagraph. The star shade will bring you closer to Earth size, planet. How accurate the spectroscopy can be done, that's something that I really can't answer. That's not my expertise. And I think there are people who can answer specifically that question. But the key point I think you are making is we'll be able to separate the light of the planet from the light of the star by using the coronagraph. And as I said, the star shade will make it even closer to looking at Earth-sized planets.
I promise, Mike, we're about to wrap up, but I want to make sure that we've got this great opportunity, these two brilliant scientists here with us today, and with Dr. Elachi's imminent retirement, I want to make sure I've got a chance to get this on the record, that one of the goals of WFIRST is to not only be able to directly image those exoplanets, but we would have the ability, from the briefing that I got at JPL, particularly with starshade, because you don't lose any photons with the starshade, to be able to spectrographically analyze that light from that Earth-like planet. Was my understanding from the scientists that briefed me at JPL, that they would be able to see the
That is
spectrographic
correct.
signature of methane and oxygen. They'd be able to see it.
I think so. I really cannot tell you 100% sure. But yes, we'll be able to do some spectroscopic measurement.
And perhaps even industrial pollution, Mike, we'll be able to see perhaps
Well, I
hydrofluorocarbons.
don't-
But nevertheless, that then leads to our kids and grandkids, and I hope one of the legacies that I would like to leave as the subcommittee chairman of this marvelous committee, and with your help, Mike, that not only have we then discovered life in an ocean, in another world, we hope in Europa, identified Earth-like planets and picked up the spectrographic signature of an atmosphere that contains methane and oxygen. But I hope also, finally in conclusion, to ask about the development of next generation of rocket propulsion, ion engines that would be able to take a spacecraft to Alpha Centauri, which is about 4.5 light years away. And if we could achieve, what percent of the speed of light do you think is possible? 2%, 4%, 5%, perhaps?
I don't know, because that requires some new invention. But I was thinking about it as I was sitting here. If I would have told my grandmother, and that's not very long ago, that's my grandmother, that I remember her when I was a kid, that I would be able to hop on a plane and fly to the United States in 12 hours, she would have thought I'm crazy. But within 100 years, we have moved from being in carriages to be able to travel across the country or across the world. So I'm sure our children will be smart enough to invent some advanced technology for propulsion to do that. Now, we need to start making some investment. We don't have an answer. I cannot tell you if you do ABC, we'll get to 1% or 2%. But also people didn't think about it for airplanes. It's by investing in the technology, we might get some new inventions that will allow us to go to those kind of
I
speeds.
think Mr. Honda has a question.
It's possible.
Right.
Well, what I'm getting from the last conversation about analyzing light sources is that will tell you the kinds of composition that on the atmosphere. Okay, because I know that planets do not emit their own light, so I was just trying to understand what we're saying here. Thank you.
Right. And then just in conclude, that is really the final piece of this hearing was to really, I hope, as a result of the time that I've got, if I have the privilege to stay here as the chairman for that time period, we will have laid the foundation not only to discover life on that other world, but to have identified those Earth-like planets around other solar systems, and then develop the rocket technology so that our children and grandchildren will have the opportunity to be witness to the first interstellar missions to Alpha Centauri. It may take 80 years or 100 years to get there, but perhaps today we have heard for the first time how we here, Mike, can lay the foundation stones for that to happen. I want to thank you very, very much for your service to the country and
Thank you.
for the time that you've given us here today, and in particular, Dr. Elachi, thank you for the extraordinary work that you've done for the Jet Propulsion Laboratory, for the nation, for NASA. Incredible discoveries that have been made on your watch, I don't think would have been possible but for your leadership. You've woven together the extraordinary talent of the scientists and engineers at JPL, but also been able to bring together the political support that was so essential to make sure that these magnificent missions were successful, and we will continue to give you all the support that we can at JPL and NASA in general. And Dr. Lunine, I want to thank you for being here as well. Thank you, Mr. Chairman. Thank you very much. The hearing is adjourned. Thank you.